Tonight, we're going to explore something that will completely change how you think about forces. You've been told your whole life that magnets push and pull, that gravity holds you down, that the ground stops your feet from falling through. But here's the thing nobody tells you. None of those forces involve anything actually touching anything else. Not really. In the deepest picture of reality that physics has ever produced, every force you've ever felt, every push, every pull, every attraction and repulsion happens because invisible particles are being exchanged between the objects involved. Forces don't just happen. They are carried, delivered, communicated through messengers that flash in and out of existence faster than anything you could ever hope to detect directly. And those messengers have a name: gauge bosons. Before we go any further, if you find this kind of deep exploration fascinating, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Let's start with something you've known your entire life. Something so basic, so obvious, that you've probably never questioned it. When you push a door, it opens. When you kick a ball, it flies. When you press your hand against a wall, the wall pushes back. Forces, at least in your everyday experience, seem to require contact. One thing touches another thing, and something happens. Energy transfers, motion changes. This is the picture of the world you grew up with. It's intuitive. It makes sense. You can feel it in your hands every time you lift a cup of coffee or throw a stone across a lake. The world seems to work through things bumping into other things. Objects collide, surfaces press together, gears mesh. Billiard balls crack against each other on a pool table and scatter in predictable directions. This contact picture of forces isn't just a casual assumption. It's been the dominant way humans have thought about physical interactions for thousands of years. Aristotle, one of the most influential thinkers in history, believed that objects required a continuous push to keep moving. In his view, a thrown spear kept flying because the air displaced from its front rushed around to push it from behind. The idea of forces acting without contact, of one object influencing another from a distance with nothing in between, would have seemed absurd to most ancient thinkers. It seemed almost magical, like believing in ghosts or invisible spirits that could reach out and grab things. Even when Isaac Newton came along in the late 1600s and described gravity as a force that acted across empty space, he was deeply uncomfortable with this idea. Newton's law of universal gravitation was spectacularly successful. It explained the orbits of the planets, the trajectory of cannonballs, the tides in the oceans. It predicted the motion of comets that wouldn't return for centuries. It was one of the greatest achievements in the history of science. But Newton himself was troubled by what his own theory seemed to imply. Gravity, according to his equations, acted instantaneously across any distance. The sun pulled the Earth. The Earth pulled the moon. And this pulling happened through apparently empty space, with nothing connecting the two objects, nothing carrying the force, nothing mediating the interaction. Newton called this action at a distance, and he didn't like it. He wrote that the idea of one body acting on another through a vacuum, without anything between them, was so great an absurdity that he believed no person who had any competent faculty of thinking could ever fall into it. Those were his words. He was essentially saying that his own theory, one of the most successful theories ever created, described something that seemed philosophically impossible. And he was right to be suspicious, not because his equations were wrong. They worked beautifully for centuries, but Because the picture they seem to paint of forces jumping magically across empty space turned out to be incomplete. There was something in between, something filling the gap, something carrying the force from one object to another. But it would take more than 200 years before physics figured out what that something was. Let's go back to that everyday experience of touching things, because even this turns out to be far stranger than it seems. When you press your hand against a table, you feel a solid surface. It feels like your hand and the table are in direct contact, atoms touching atoms, skin against wood. But here's what's actually happening at the atomic level. Your hand is made of atoms, the table is made of atoms, and atoms are mostly empty space. If you could zoom into an atom, you'd find a tiny nucleus at the center containing protons and neutrons. Surrounding that nucleus, at a relatively enormous distance, are electrons. The nucleus of an atom is incredibly small compared to the atom as a whole. If the atom were the size of a football stadium, the nucleus would be about the size of a marble sitting on the 50-yard line. Everything else in that stadium is empty. The electrons aren't little balls orbiting the nucleus like planets around the sun. They exist as probability clouds, smeared out across the atom's volume. But the key point is this: atoms are overwhelmingly empty. The solid matter you experience every day, the table, the floor, your own body, is almost entirely nothing. Empty space with tiny points of concentrated mass scattered incredibly far apart relative to their size. So when your hand presses against the table, what's actually happening? Are there atoms in your hand touching the atoms in the table? No, they're not. They never touch, not even close. What you feel as the solid resistance of the table is actually electromagnetic repulsion between the electron clouds of your hand's atoms and the electron clouds of the table's atoms. The electrons in your skin and the electrons in the table surface are both negatively charged, and like charges repel each other. As the atoms in your hand approach the atoms in the table, the electromagnetic force between the electron clouds pushes back, creating the sensation of solidity, of contact, of touching. But there's a gap. There's always a gap. The atoms never actually come into contact in any direct mechanical sense. The force you feel is electromagnetic, and it's being mediated across that tiny gap by something. The sensation of touching is an illusion created by forces acting across a distance, even if that distance is unimaginably small. This might seem like a philosophical distinction rather than a practical one. After all, what's the difference between actually touching something and being repelled by electromagnetic force at a distance so small you could never perceive it? In everyday life, there's no practical difference, but in physics, this distinction matters enormously, because it tells us something fundamental about the nature of forces. Even the most seemingly direct contact force, the simple act of pushing your hand against a solid surface, isn't really contact at all. It's a field interaction. It's one set of charged particles influencing another set of charged particles through the electromagnetic field that fills the space between them. And that word, field, is the key to everything that comes next. A field in physics is something that has a value at every point in space. You can think of it as an invisible medium that permeates everything. Temperature is a kind of field. At every point in a room, there's a temperature value. Some spots are warmer, some are cooler. If you walked around the room with a thermometer, you'd measure a temperature at every location. That collection of values across space is a temperature field. But temperature isn't a fundamental field in physics. It's a statistical property of how atoms are moving. The fields we're talking about in fundamental physics are more basic than that. They're not emergent properties of something else. They're the foundational ingredients of reality itself. The electromagnetic field is the most familiar example. It exists everywhere in the universe. At every point in space, there's an electromagnetic field with a particular value and direction. When you turn on a light, when a radio station broadcasts a signal, when your microwave heats your food, what's happening is that the electromagnetic field is oscillating. Waves are traveling through it. Those waves are what we call electromagnetic radiation. And depending on their frequency, we experience them as radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, or gamma rays. All of these are the same fundamental phenomenon, oscillations in the electromagnetic field. This was one of the great insights of 19th century physics. James Clerk Maxwell, a Scottish physicist working in the 1860s, unified electricity and magnetism into a single framework. He showed that electric fields and magnetic fields aren't separate things. They're two aspects of one underlying field, the electromagnetic field. And he showed that disturbances in this field propagate through space as waves traveling at the speed of light. In fact, light itself is an electromagnetic wave. This was a revolutionary discovery. It connected optics, electricity, and magnetism into one coherent picture. But Maxwell's theory also did something else. It provided a mechanism for how charged particles influence each other. In Newton's picture of gravity, forces seem to act magically across empty space. In Maxwell's picture of electromagnetism, forces act through a field. An electric charge creates a disturbance in the electromagnetic field around it. That disturbance spreads outward through the field. When another charge encounters this disturbance, it responds. It feels a force. The field is the intermediary, the carrier, the medium through which the interaction occurs. This was a huge conceptual advance. Forces don't jump across empty space, they propagate through fields. The field fills the gap between the two interacting objects. There's no magical action at a distance. There's a field, and the field carries the influence from one place to another. But this raised a new question. If the electromagnetic field carries the force, what exactly is the field made of? What is it? In the 19th century, physicists tried to answer this by proposing the luminiferous ether, a hypothetical substance that filled all of space and served as the medium through which light waves traveled, just as sound waves travel through air. But the famous Michelson-Morley experiment in 1887 failed to detect any such ether. Light didn't seem to need a medium. The electromagnetic field just existed on its own, as a fundamental feature of the universe, not as a vibration in some underlying substance. This left physicists in an uncomfortable position. Fields were clearly the right way to think about forces. They solved the action at a distance problem. But the fields themselves were mysterious. What were they really? The answer wouldn't come until the 20th century, when quantum mechanics changed everything. In the early 1900s, physics underwent two revolutions almost simultaneously. One was Einstein's theory of relativity, which showed that space and time are intertwined and that the speed of light is a universal constant. The other was quantum mechanics, which revealed that at the smaller scales, that the world is fundamentally different from what our everyday experience suggests. Energy comes in discrete packets called quanta. Particles can behave like waves. Waves can behave like particles. The act of measurement affects what you're measuring. Reality at the quantum level is probabilistic, not deterministic. These two revolutions eventually merged into what we now call quantum field theory. And this is where the story of gauge bosons truly begins. Quantum field theory starts with a radical idea. Everything in the universe, every particle you've ever heard of, is actually an excitation of an underlying field. An electron isn't a little ball floating in empty space. It's a localized vibration, an excitation in the electron field. This electron field exists everywhere, at every point in the universe. Most of the time, at most locations, the field is in its lowest energy state, its ground state. Nothing's happening. But when energy is added to the field in the right way, a ripple forms. That ripple is what we detect as an electron. The same is true for every other particle. There's a quark field, and quarks are excitations of that field. There's a muon field, and muons are excitations of it. Every type of fundamental particle has its own corresponding field that permeates all of space. Particles aren't things that exist in fields. Particles are the fields, or more precisely, they're what happens when the fields get excited. This is a profound shift in how we think about reality. The fundamental ingredients of the universe aren't particles, they're fields. Particles are just what fields do when they're disturbed. They're the observable, quantized excitations of something deeper and more fundamental. Think of a calm ocean. The ocean represents the field in its ground state. Nothing visible, nothing special happening. Now drop a stone into the ocean. A wave forms. That wave is a localized disturbance in the water. It travels. It carries energy. And if you only looked at the wave without knowing about the ocean, you might think the wave was the fundamental thing. But the ocean was there all along. The wave is just what the ocean does when it's disturbed. Similarly, a particle is just what a quantum field does when it's excited. Now, here's where it gets really interesting. The same framework that describes matter particles also describes forces. Just as there's an electron field whose excitations are electrons, there's an electromagnetic field whose excitations are photons. The photon is a quantum of the electromagnetic field. A discrete packet of electromagnetic energy, a particle of light. When two electrons repel each other, what's happening at the quantum level is that the electromagnetic field between them is being disturbed. Quanta of this field, photons, are being exchanged between the two electrons. These exchanged photons are what carry the force. They're the messengers, the intermediaries, the things that communicate the interaction from one charged particle to another. This is the crucial insight. Forces in quantum field theory are not mysterious pushes and pulls that happen at a distance. They are the result of particles exchanging other particles. The force-carrying particles are the quanta of the force field, and they mediate the interaction between the matter particles. Every force has its own field, and every force field has its own quanta. These quanta, these messenger particles, are what physicists call gauge bosons. Let's slow down and make sure this is really clear, because this idea is the foundation of everything else we're going to explore. Imagine two people standing on a frozen lake, facing each other. One person throws a heavy ball to the other. When the first person throws the ball, they recoil backward from the throw. When the second person catches the ball, they're pushed backward by the impact. Both people have been pushed apart. If you were watching from above and couldn't see the ball, you'd think some invisible force was pushing the two people away from each other. You'd see them moving apart and you'd conclude there was a repulsive force between them. But the reality is that the force was carried by the ball. The ball was the messenger. It transferred momentum from one person to the other. This is a rough and imperfect analogy for how gauge bosons work. Two charged particles, say two electrons, interact by exchanging gauge bosons, in this case, photons. The photons carry momentum and energy between the electrons. The result is that the electrons are pushed apart. The electromagnetic force between them is repulsive because they have the same charge, and the exchange of photons is the mechanism by which this repulsion occurs. Now, I said this analogy is rough and imperfect, and it is. Real gauge boson exchange is a quantum mechanical process that doesn't map perfectly onto the picture of throwing a ball. For one thing, the exchanged photons in a force interaction aren't the same as the photons you see with your eyes. The photons that carry forces between charged particles are called virtual photons. They're a different kind of excitation than the real photons that travel through space and enter your eyes. Virtual particles don't obey the same energy-momentum relationships as real particles. They exist fleetingly as part of the quantum interaction, doing their job of transferring force and then vanishing. You can't detect a virtual photon directly with any instrument, but their effects are very real and measurable. Also, the ball throwing analogy doesn't easily explain attractive forces. If two people are throwing balls at each other, they'll be pushed apart. But electromagnetism can also be attractive. Opposite charges attract. How does exchanging particles lead to attraction? The answer involves the full quantum mechanical treatment, which is mathematically complex. But the short version is that the nature of the quantum exchange allows for both repulsion and attraction, depending on the properties of the particles involved. The mathematics of quantum field theory handles this naturally, even if the simple ball-throwing picture doesn't capture it. The important point is this: forces between fundamental particles don't happen through direct contact. They don't happen through magical action at a distance. They happen through the exchange of gauge bosons, the quanta of the force fields. The electromagnetic force is carried by photons. The strong nuclear force, the force that holds protons and neutrons together inside atomic nuclei, is carried by particles called gluons. The weak nuclear force, responsible for certain types of radioactive decay, is carried by particles called W and Z bosons. Each force has its own messenger. Each messenger is the quantum of a specific gauge field. And gravity? Gravity is expected to be carried by a particle called the graviton, but the graviton has never been detected, and gravity doesn't yet fit comfortably into the quantum field theory framework. It remains the one fundamental force that we haven't successfully described using gauge bosons. This is one of the great unsolved problems in physics. But for the three forces that the standard model of particle physics does describe, electromagnetism, the strong force, and the weak force, the gauge boson picture works with extraordinary precision. Let me give you a sense of how precise. Quantum electrodynamics, the quantum field theory of electromagnetism, makes predictions that have been verified experimentally to more than 10 decimal places. The magnetic moment of the electron, a measure of how the electron interacts with magnetic fields, has been calculated using quantum electrodynamics and measured in laboratories. The theoretical prediction and the experimental measurement agree to a precision of about 1 part in 10 billion. This is the most precisely tested prediction in the entire history of science. And it's built on the idea that electromagnetic forces are mediated by the exchange of photons, the gauge bosons of electromagnetism. This level of agreement between theory and experiment isn't a coincidence. It's telling us something deep about reality. The gauge boson picture of forces isn't just a useful model or a convenient way of thinking about things. It's a description of how nature actually works at the most fundamental level. Forces really are carried by messenger particles. Interactions really do occur through the exchange of quanta of gauge fields. This is not metaphor, this is the mechanism. So let's step back and take stock of where we are. We started with the everyday intuition that forces require contact. We discovered that even what we call contact is really electromagnetic repulsion at the atomic level. We saw that forces act through fields, invisible entities that permeate all of space. We learned that in quantum field theory, everything, both matter and forces, arises from quantum fields. Matter particles like electrons and quarks are excitations of matter fields. Force-carrying particles, gauge bosons, are excitations of gauge fields. And forces between matter particles occur through the exchange of these gauge bosons. Every fundamental interaction in the universe is a conversation between fields. When an electron emits a photon and another electron absorbs it, that's a conversation. When quarks inside a proton exchange gluons billions of times per second, holding the proton together, that's a conversation. When a neutron decays into a proton by emitting a W boson, which then decays into an electron and an anti-neutrino, that's a conversation. The universe is not made of stuff that pushes and pulls. The universe is made of fields that talk to each other, and gauge bosons are the words. This picture of reality is one of the greatest achievements of 20th century physics. It took decades to develop, involving some of the most brilliant minds in history. People like Paul Dirac, who first merged quantum mechanics with special relativity, Richard Feynman, Julian Schwinger, and Shinichiro Tomonaga, who developed quantum electrodynamics and shared a Nobel Prize for it. Chen-Ning Yang and Robert Mills, who generalized the gauge principle to describe the strong and weak forces. Sheldon Glashow, Abdus Salam, and Steven Weinberg, who unified the electromagnetic and weak forces into a single framework. And many, many others who contributed pieces to this enormous puzzle. The result of all this work is the standard model of particle physics. It's the most successful theory of fundamental physics ever constructed. It describes 3 of the 4 known forces of nature: electromagnetism, the strong force, and the weak force. It accounts for all known fundamental particles, and at its core, at its absolute foundation, is the idea that forces arise from the exchange of gauge bosons. But what exactly makes a gauge boson a gauge boson? What properties do these messenger particles have? What distinguishes them from the matter particles they interact with? And why is the word gauge attached to them at all? What does gauge symmetry mean? And why is it so important? Those questions will take us deeper into the heart of the universe's structure. Because understanding what a gauge boson really is doesn't just mean knowing its name or memorizing which force it carries. It means understanding why it must exist. Why the universe would be mathematically inconsistent without these messenger particles. Why the very symmetries that govern reality demand their presence. And that's where this story gets truly extraordinary. Now, we need to get precise about what a gauge boson actually is. Not just the vague idea that it carries a force, not just the metaphor of a messenger delivering a letter. We need to understand what makes these particles fundamentally different from the matter particles they interact with. Because the distinction between force carriers and matter particles isn't just a label. It's built into the deepest structure of quantum mechanics. It comes down to a single property that divides the entire particle kingdom into two completely separate categories. That property is called spin. Now, spin in particle physics is not what you think it is. It has nothing to do with a particle physically rotating like a spinning top or a basketball on someone's finger. Particles, as far as we know, are point-like. They don't have a surface that can rotate. They don't have an axis you can watch turning. And yet, every fundamental particle in the universe carries a quantity that physicists call spin. And this quantity behaves mathematically exactly like angular momentum, the physics of rotating things. A particle with spin responds to magnetic fields in specific ways. It contributes angular momentum to any system it's part of. It obeys rules about how it can combine with other spinning particles. Spin is as real as mass or charge. You can measure it, you can predict its effects, but it's an intrinsic property of the particle, not a description of physical rotation. It's a quantum mechanical property with no direct analogy in everyday life. You just have to accept that particles carry this property called spin, measured in units of a fundamental constant called the reduced Planck constant, and that spin determines almost everything about how a particle behaves. Here's where it matters. All fundamental particles fall into one of two categories based on their spin. Particles with half-integer spin, meaning their spin value is 1/2, 3/2, 5/2, and so on, are called fermions. Particles with integer spin, meaning their spin value is 0, 1, 2, and so on, are called bosons. This division is absolute. There are no exceptions. Every particle ever discovered or theorized falls into one of these two groups, and the group it belongs to determines its fundamental behavior. Fermions are the matter particles. Electrons have a spin of 1/2. Quarks have a spin of 1/2. Neutrinos have a spin of 1/2. Protons, which are made of quarks, behave as fermions. Neutrons, also made of quarks, behave as fermions. The particles that make up the physical stuff of the universe, the building blocks of atoms and molecules and everything you can see and touch, are all fermions. Every one of them has half-integer spin. Bosons are the force carriers and certain other special particles. Photons have a spin of 1. Gluons have a spin of 1. The W and Z bosons have a spin of 1. All the gauge bosons, every single one of them, have a spin of exactly 1. They're all spin 1 particles. The Higgs boson, which we'll talk about later, has a spin of 0. The hypothetical graviton, if it exists, would have a spin of 2. These are all bosons because they all have integer spin, but the gauge bosons specifically are the spin 1 particles associated with fundamental forces. Now, why does this distinction matter so much? Because fermions and bosons obey completely different rules about how they can coexist in the same quantum state. This difference governs literally everything about how the universe is structured. Fermions obey what's called the Pauli exclusion principle, named after the Austrian physicist Wolfgang Pauli. This principle states that no two identical fermions can occupy the same quantum state at the same time. Two electrons in an atom cannot have exactly the same set of quantum numbers. If one electron is in a particular energy level with a particular spin orientation, no other electron can be in that exact same state. This is why electrons and atoms arrange themselves in shells. The first shell fills up, and additional electrons are forced into higher energy shells because the lower shells are already occupied. This is why the periodic table of elements has the structure it does. This is why chemistry works the way it does. This is why matter has volume and resists being compressed. The Pauli exclusion principle prevents fermions from piling up in the same state, and this creates the rich, complex structure of atoms, molecules, and everything built from them. Without the exclusion principle, all electrons would collapse into the lowest energy state, and atoms as we know them wouldn't exist. Chemistry wouldn't exist. You wouldn't exist. Bosons obey completely different rules. They follow what's called Bose-Einstein statistics, named after Satyendranath Bose and Albert Einstein. The key feature of Bose-Einstein statistics is that there is no exclusion principle for bosons. Multiple identical bosons can occupy the same quantum state simultaneously. In fact, bosons actually prefer to be in the same state. The more bosons that are already in a given state, the more likely it is that another boson will join them. This is the opposite of fermions. Where fermions avoid each other, bosons crowd together. This difference has enormous consequences. For gauge bosons, the ability to pile into the same quantum state is what allows forces to behave the way they do. Consider electromagnetism. When a powerful magnet exerts a force, that force is being mediated by photons, the gauge bosons of electromagnetism. At the quantum level, an enormous number of virtual photons are being exchanged between the charged particles in the magnet and the charged particles in whatever object the magnet is attracting or repelling. These photons can all occupy the same state because they're bosons. There's no limit to how many photons can participate in the interaction. This is what allows electromagnetic forces to be strong and long-ranged. Countless photons can pile up, all working together, all reinforcing each other, creating a coherent macroscopic force that you can feel with your hands. If photons were fermions, subject to the Pauli exclusion principle, only one photon could occupy each quantum state. The electromagnetic force would behave completely differently. You wouldn't be able to create strong magnetic fields or coherent beams of light. Lasers wouldn't work, because a laser depends on getting enormous numbers of photons into exactly the same quantum state. The entire character of electromagnetism would change. The universe would be unrecognizable. So the fact that gauge bosons are bosons with integer spin and the ability to occupy the same quantum state in unlimited numbers is not an incidental detail. It's essential to how forces work. It's what makes forces forces. The bosonic nature of the messenger particles is what allows them to build up and create the coherent, macroscopic forces we observe in nature. Now, let's address the other half of the name, the word gauge. This is where things get deeper and more beautiful, because the word gauge connects these particles to one of the most powerful ideas in all of physics, symmetry. In everyday life, symmetry means something looks the same after a transformation. A circle is symmetric because you can rotate it by any angle and it looks identical. A square is symmetric under rotations of 90 degrees. A human face is roughly symmetric under reflection. The left side looks approximately like the right side. In physics, symmetry means something much more profound. A physical system has a symmetry if you can perform a certain transformation on it, and the laws of physics remain unchanged. The outcome of any experiment, the behavior of any particle, the evolution of any system stays exactly the same after the transformation. One of the simplest symmetries in physics is translational symmetry. The laws of physics are the same whether you do your experiment in New York, in Tokyo, on Mars, or in another galaxy. You can shift your location anywhere in the universe, and the fundamental laws don't change. This symmetry is connected to the conservation of momentum. Another is rotational symmetry. The laws of physics don't care which direction you're facing. You can rotate your experiment to point in any direction, and the results will be the same. This is connected to the conservation of angular momentum. These connections between symmetries and conservation laws were formalized in one of the most beautiful theorems in all of physics, proved in 1918 by the mathematician M.E. Noether. Noether's theorem states that every continuous symmetry of the laws of physics corresponds to a conserved quantity. Translational symmetry gives you conservation of momentum. Rotational symmetry gives you conservation of angular momentum. Time symmetry, the fact that the laws of physics don't change over time, gives you conservation of energy. These connections are deep and universal. Now, the symmetries I just described are called global symmetries. They involve performing the same transformation everywhere in the universe simultaneously. You shift everything in the universe by the same amount. You rotate everything by the same angle. The transformation is uniform across all of space and time. Gauge symmetry is different. It's a local symmetry. It means you can perform a transformation that varies from point to point in space and time, and the physics still doesn't change. You're not doing the same transformation everywhere. You're doing a different transformation at every location. And the laws of physics still remain unchanged. This is a much stronger requirement than global symmetry. And here's the critical part. When you demand that a theory have local gauge symmetry, when you insist that the physics remains unchanged under these local transformations, something remarkable happens. The mathematics forces you to introduce new fields. You can't have a gauge-symmetric theory of matter particles without also having force-carrying fields. The gauge fields, and their quanta, the gauge bosons, aren't optional extras that physicists decided to add to their theories for convenience. They're mathematically required. If you write down a theory of electrons and demand that the theory respects a certain local gauge symmetry, the equations won't be consistent unless you also include the electromagnetic field. The photon must exist if the gauge symmetry is to hold. It's not a choice. It's a mathematical necessity. Let me try to make this more concrete. Consider the electron field. In quantum mechanics, the electron is described by a mathematical object called a wave function. This wave function has a property called phase, which you can think of as an internal angle. The physical predictions of quantum mechanics, the probabilities of finding the electron in various places, depend only on the magnitude of the wave function, not on its phase. This means you can change the phase of the wave function everywhere by the same amount, and nothing physically changes. That's a global symmetry. But what if you want to change the phase by different amounts at different locations? What if you want the freedom to adjust the phase independently at every point in space? That's a local gauge transformation. And if you try to do this with just the electron field alone, the mathematics breaks. The equations become inconsistent because changing the phase at different rates at different locations introduces extra terms that don't cancel out. The theory stops making correct predictions. The fix is to introduce a new field, a gauge field, that compensates for these extra terms. This gauge field transforms in a specific way under the local transformation, exactly cancelling the problematic terms and restoring the consistency of the theory. In the case of the electron and its phase symmetry, the required gauge field is the electromagnetic field. The photon is the quantum of this field. And the interaction between the electron and the photon, the coupling between the matter field and the gauge field, is what we experience as the electromagnetic force. This is breathtaking when you think about it. You start by saying that the laws of physics should look the same regardless of how you adjust an internal property of the electron field from point to point in space. This seems like a reasonable, even elegant requirement. And this simple demand for local symmetry forces the existence of the electromagnetic field and its quantum, the photon. The photon doesn't just happen to exist. It has to exist. The symmetry demands it. This is what the word gauge means in gauge boson. These particles are the quanta of fields that arise from gauge symmetries. They're the mathematical consequence of demanding that the laws of physics remain invariant under local transformations. Every gauge boson in the standard model exists because a specific local symmetry demands it. Now let's look at the photon specifically, because it's the simplest and most intuitive gauge boson. It's the one we interact with constantly in everyday life, and the one whose behavior we understand most completely. The photon is the gauge boson of electromagnetism. It's the quantum of the electromagnetic field. Every electromagnetic interaction at the quantum level involves photons. When you see light, photons are entering your eyes and being absorbed by the photoreceptor cells in your retina. When a radio picks up a signal, it's detecting photons at radio frequencies. When your skin feels warmth from the sun, that's photons in the infrared range transferring energy to the molecules in your skin. The photon has several distinctive properties. First, it's massless. This is not just an approximation. The photon has exactly 0 rest mass. This is why light travels at the speed of light. If photons had mass, even an incredibly tiny amount, light would travel slower than the current speed of light, and the properties of electromagnetism would be different. The fact that the photon is massless is directly related to the unbroken gauge symmetry of electromagnetism. As long as the symmetry remains unbroken, the gauge boson must be massless. This is a general principle. Unbroken gauge symmetries produce massless gauge bosons. We'll see later how broken gauge symmetries can produce massive gauge bosons, like the W and Z bosons, but that's a different part of the story. Second, the photon has a spin of 1. This makes it a vector boson. The spin determines the mathematical structure of the field and the way the photon interacts with matter. A spin 1 particle has specific polarization states, and these polarization states correspond to the directions in which the electromagnetic field oscillates. This is what gives light its polarization properties. When you wear polarized sunglasses, you're filtering out photons whose polarization is oriented in a particular direction. Third, the photon is electrically neutral. It carries no electric charge. This means the photon doesn't interact with other photons through electromagnetism. Photons pass through each other without scattering. This is why 2 flashlight beams can cross in midair without affecting each other. Each beam continues on its way as if the other beam weren't there. This property arises because the photon is the gauge boson of a symmetry group called U1, which is an abelian group, meaning its elements commute with each other. In less technical language, the electromagnetic field's gauge transformations don't interact with each other, and neither do the photons. Fourth, because the photon is massless, the electromagnetic force has infinite range. A photon can travel forever through empty space without losing energy or decaying. This is why you can see stars that are billions of light years away. The photons they emitted have been traveling through space for billions of years and still arrive at your eyes carrying the information about those distant stars. The infinite range of the electromagnetic force is a direct consequence of the photon having zero mass. Forces carried by massive bosons have limited range. Forces carried by massless bosons have unlimited range. This relationship between boson mass and force range is one of the most important principles in particle physics. Now, I mentioned virtual particles earlier, and this concept deserves more attention because it's central to how gauge bosons actually mediate forces. When two electrons interact electromagnetically, what happens at the quantum level is that one electron emits a virtual photon, and the other electron absorbs it. The photon travels from one electron to the other, carrying momentum and energy. And the result is that both electrons experience a change in their motion. This is the exchange process. But here's what makes virtual photons different from the real photons we detect with our eyes and instruments. A real photon is an excitation of the electromagnetic field that propagates freely through space. It has a definite relationship between its energy and its momentum. Specifically, for a massless particle like the photon, its energy equals its momentum times the speed of light. This is called being on shell. Real particles are always on shell. They satisfy the energy-momentum relationship dictated by their mass. Virtual photons don't satisfy this relationship. They can have any combination of energy and momentum. They can even have a mass-like quality, despite the real photon being massless. This is allowed because virtual particles exist only for a very short time. So short that the uncertainty principle permits them to violate the normal energy-momentum relationship temporarily. The more a virtual particle deviates from the on-shell condition, the shorter its lifetime and the shorter the distance it can travel. This is why virtual particles are not directly detectable. They exist for fleeting instants as part of the interaction process and then disappear. But let me be very clear about something. Virtual particles are not just a convenient mathematical fiction. They produce real, measurable effects. The Lamb shift, a tiny displacement in the energy levels of hydrogen, was one of the first experimental confirmations of virtual particle effects. It was measured by Willis Lamb and Robert Rutherford in 1947, and it agreed precisely with the predictions of quantum electrodynamics, which calculate the effects of virtual photons, and virtual electron-positron pairs on the hydrogen atom's energy levels. The Casimir effect is another measurable consequence of virtual particles. Two uncharged conducting plates placed very close together in a vacuum experience a tiny attractive force. This force arises because the virtual photons that can exist between the plates are restricted by the boundary conditions. Fewer virtual photons fit between the plates than outside them. The resulting imbalance creates a measurable pressure that pushes the plates together. This effect has been measured experimentally and agrees with theoretical predictions. So virtual gauge bosons are real in the sense that matters most in physics. They produce effect you can measure. They're the mechanism by which forces operate at the quantum level. There's a beautiful visual language that physicists use to describe these interactions. They're called Feynman diagrams, named after the physicist Richard Feynman, who invented them in the late 1940s. Feynman diagrams are simple pictures that represent quantum interactions. In a Feynman diagram, matter particles like electrons are drawn as straight lines. Gauge bosons like photons are drawn as wavy lines. The points where lines meet, called vertices, represent interactions: an electron emitting a photon, an electron absorbing a photon, two quarks exchanging a gluon. These pictures aren't just artistic representations. Each diagram corresponds to a precise mathematical expression. The lines and vertices translate directly into equations that let you calculate the probability of any given interaction occurring. This is the power of Feynman diagrams. They're a visual language that maps perfectly onto the mathematical structure of quantum field theory. The simplest electromagnetic interaction is the exchange of a single virtual photon between two charged particles. In a Feynman diagram, you draw two straight electron lines approaching each other. At some point, one electron line emits a wavy photon line, and the other electron line absorbs it. The electrons then continue on, but their momenta have changed. They've been deflected by the exchange. This single photon exchange gives you the leading contribution to the electromagnetic force between two charges. But it's not the whole story. Quantum field theory tells you that you also have to consider more complicated diagrams. What if the exchanged photon temporarily splits into a virtual electron-positron pair, which then annihilates back into a photon? That's a valid process, and it contributes to the interaction. What if two photons are exchanged instead of one? What if one of the photons emits and reabsorbs another virtual photon along the way? All of these more complicated processes contribute to the total interaction, and you have to add them all up. This is the method of perturbation theory. You start with the simplest diagram and then add corrections from more and more complicated diagrams. Each additional complication is typically smaller than the previous one, so the series converges. The sum of all these contributions gives you the precise prediction that you compare with experiment. And for quantum electrodynamics, this sum matches what laboratories actually measure to a degree of accuracy that no other theory in any field of science has ever achieved. Feynman diagrams also reveal something philosophically fascinating. At the quantum level, an interaction between two particles isn't a single, definite process. It's the sum of all possible processes. The photon that mediates the force between two electrons isn't just one photon traveling along one path. It's the superposition of every possible way the interaction could happen. One photon, two photons, three photons. Photons that split into particle-antiparticle pairs. Photons that loop around and interact with themselves. Every possible history contributes to the final result. The actual interaction is the sum of all these possibilities, weighted by their probabilities. This is the path integral formulation of quantum mechanics, one of Feynman's deepest contributions to physics. Let's pause and bring all of this together. A gauge boson is a fundamental particle with integer spin, specifically spin 1, that arises as the quantum of a gauge field. Gauge fields exist because local gauge symmetries demand them. These symmetries are the requirement that certain internal transformations of the matter fields can vary from point to point in space without changing the physics. When you impose this requirement on a theory, the mathematics generates gauge fields automatically. The quanta of these fields, the gauge bosons, are the messenger particles that mediate fundamental forces. The photon is the simplest and most familiar gauge boson. It's massless, spin 1, electrically neutral, and it mediates the electromagnetic force. It arises from the U1 gauge symmetry of electromagnetism. The masslessness of The photon is a direct consequence of this symmetry being unbroken. Gauge bosons carry forces by being exchanged between matter particles as virtual particles. These exchanges produce real, measurable effects, even though the virtual particles themselves can't be directly observed. The entire process can be visualized and calculated using Feynman diagrams, which provide both an intuitive picture and a precise mathematical framework. And underlying all of this is the principle of gauge symmetry, the idea that the laws of physics should be invariant under local transformations. This principle doesn't just allow gauge bosons to exist, it requires them. It demands their existence as a mathematical necessity. Without gauge bosons, the gauge symmetries that underpin the standard model would be broken, and the theory would collapse into inconsistency. The photon is the prototype, the template, the clearest example of how a gauge boson works. But it's not the only one. The universe has other forces, and those forces have their own gauge bosons with their own peculiar properties. Some are massless like the photon, some are not. Some carry the charge of the force they mediate, some don't. The full roster of gauge bosons is stranger and more varied than the photon alone might suggest. And understanding those other gauge bosons will take us into some of the most extreme environments in the universe. Inside the nuclei of atoms, where the strong force holds quarks together with a grip so tight that nothing can break it. Into the heart of dying stars, where the weak force transforms one type of particle into another, powering the nuclear reactions that forge the elements of the periodic table. Into the moments just after the Big Bang, when the forces that now seem so different were once unified into a single interaction, mediated by gauge bosons that have since gone their separate ways. The photon showed us the principle. Now we need to see how nature applied that principle to build the rest of the universe. The photon is the gauge boson most people encounter in everyday life, even if they don't realize it. Every time you flip a light switch, look at your phone screen, feel the warmth of sunlight, or use a microwave oven, you're interacting with photons. Electromagnetism is the force that governs the world at human scales. It holds atoms together, powers chemical reactions, and makes light possible. But electromagnetism is not the only force in nature. There are others. And their gauge bosons are stranger, more exotic, and in some ways more fascinating than the photon. Let's go deep inside the atom, past the electron clouds that surround the nucleus, past the electromagnetic interactions that bind electrons to atoms, down into the nucleus itself, where protons and neutrons are packed together in an incredibly tiny space. The nucleus of an atom is about 100,000 times smaller than the atom itself. All the mass of the atom is crammed into a volume that is trillions of times smaller than the atom's overall size. And yet, this tiny core contains almost all the atom's mass. The protons and neutrons are squeezed together at densities that are almost impossible to comprehend. A teaspoon of nuclear material would weigh about 4 billion tons. Now, here's the problem. Protons are positively charged. They all carry the same electric charge. And like charges repel each other through the electromagnetic force, every proton in a nucleus is electromagnetically repelling every other proton. In a heavy element like uranium, there are 92 protons crammed into an absurdly tiny space, all pushing against each other with enormous force. The electromagnetic repulsion between these protons is immense. So what holds the nucleus together? What prevents it from flying apart? The answer is the strong nuclear force, and the strong force is carried by gauge bosons called gluons. The strong force is the most powerful force in nature. After the distances relevant inside a nucleus, it's about 100 times stronger than the electromagnetic force. It overwhelms the electromagnetic repulsion between protons and binds the nucleus together with a grip so powerful that it takes extraordinary amounts of energy to break it. This is why nuclear reactions release so much energy. When you split a heavy nucleus in nuclear fission or fuse light nuclei in nuclear fusion, you're fighting against or rearranging the bonds created by the strong force. The energy stored in those bonds is enormous, but the strong force doesn't act directly on protons and neutrons as whole objects. It acts on something deeper. Protons and neutrons are not fundamental particles. They're made of smaller particles called quarks. A proton contains 3 quarks, 2 up quarks, and 1 down quark. A neutron also contains 3 quarks, 2 down quarks, and 1 up quark. The strong force is fundamentally a force between quarks, and gluons are the particles that carry it. Gluons are gauge bosons with spin 1, just like the photon. They arise from a gauge symmetry, just like the photon, but that's where the similarities with the photon end. Because gluons are different from photons in ways that are profoundly important and deeply strange. The first major difference is the type of charge involved. Electromagnetism involves electric charge, which comes in 2 varieties, positive and negative. The strong force involves a different type of charge called color charge. Color charge comes in 3 varieties, which physicists have labeled red, green, and blue. These names have absolutely nothing to do with actual colors. Quarks are far too small to have any visual color. The names are just labels for the 3 types of strong force charge. Each quark carries one of these 3 color charges. Antiquarks carry the corresponding anticolors: anti-red, anti-green, and anti-blue. The theory that describes the strong force is called quantum chromodynamics, often shortened to QCD. The word chromo comes from the Greek word for color, reflecting the color charge that the theory describes. Now, here's the first strange thing about gluons that makes them fundamentally different from photons. The photon is electrically neutral. It doesn't carry the charge of the force it mediates. This means photons don't interact with other photons through electromagnetism. 2 beams of light pass through each other without any effect. But gluons are not neutral with respect to color charge. Gluons themselves carry color charge. Each gluon carries a combination of a color and an anticolor. For example, a gluon might carry red anti-blue or green anti-red. Because gluons carry the very charge they mediate, gluons interact with other gluons. They don't just carry the strong force between quarks, they also exert the strong force on each other. This self-interaction of gluons has enormous consequences. It's what makes a strong force so dramatically different from electromagnetism. In electromagnetism, the force between 2 charges gets weaker as they move farther apart. Double the distance and the force drops to 1/4 of its original strength. This is the familiar inverse square law. The electromagnetic force weakens smoothly and gradually with distance. You can always separate 2 charges if you pull hard enough. The strong force doesn't work like this at all. At very short distances, inside a proton or neutron, quarks experience relatively little force. They move around almost freely. This property is called asymptotic freedom, and its discovery by David Gross, Frank Wilczek, and David Politzer earned them the Nobel Prize in Physics in 2004. At short distances, quarks behave almost like free particles. The strong force is weak at close range. But as quarks try to move farther apart, something extraordinary happens. The force between them doesn't weaken, it gets stronger. The gluon field between two separating quarks doesn't spread out and dissipate like the electromagnetic field between separating charges. Instead, because gluons interact with each other, the field lines between the quarks get squeezed into a narrow tube, a string of gluon energy connecting the two quarks. As the quarks move apart, this string stretches, and the energy stored in it increases. You're pulling against a force that grows stronger the farther you pull. Eventually, if you put enough energy into pulling the quarks apart, something dramatic happens. The energy stored in the gluon string becomes so great that it's enough to create a new quark-antiquark pair out of the vacuum. The string snaps, but instead of getting two isolated quarks, you get two pairs of quarks. The original quarks are still bound together with new partners. You never get a free quark. You always end up with quarks combined into composite particles. This phenomenon is called confinement. Quarks are permanently confined inside composite particles. No experiment has ever isolated a single free quark, and the theory of quantum chromodynamics predicts that no experiment ever will. Quarks always come in groups, bound together by gluons. The particles they form are called hadrons. Protons and neutrons are the most familiar hadrons, but there are hundreds of others, most of them unstable, produced briefly in particle accelerator experiments, before decaying into more stable configurations. Confinement is a direct result of gluon self-interaction. Because gluons carry color charge and interact with each other, the gluon field between quarks behaves completely differently from the photon field between charges. The photon field spreads out smoothly, getting weaker with distance. The gluon field concentrates into strings that get stronger with distance. This single difference, arising from the fact that gluons carry the charge they mediate while photons do not, creates two forces with completely different characteristics. Another consequence of gluon self-interaction is that the strong force has a very short range, despite gluons being massless. This might seem contradictory. The photon is massless and the electromagnetic force has infinite range. The gluon is also massless, so you might expect the strong force to also have infinite range. But confinement prevents this. Because quarks and gluons are confined inside hadrons, the strong force doesn't extend far beyond the boundaries of these particles. At distances larger than about 1 femtometer, roughly the size of a proton, the strong force between individual quarks is screened by the confining mechanism. What leaks out beyond the proton is a residual force, a shadow of the full strong force, which is what holds protons and neutrons together in the nucleus. This residual nuclear force is much weaker than the fundamental strong force between quarks, and it falls off rapidly with distance. There's another detail about gluons worth mentioning. While the photon comes in exactly one type, gluons come in 8 types. This number arises from the mathematics of the symmetry group that governs the strong force. The strong force is based on a gauge symmetry called SU3, which describes transformations among 3 color charges. The mathematics of SU3 requires exactly 8 independent gauge bosons. 8 gluons, each carrying a different combination of color and anti-color charges. These 8 gluons constantly fly back and forth between quarks inside every proton, every neutron, every hadron in the universe. The inside of a proton is a seething, chaotic environment. Quarks and gluons are constantly interacting, exchanging color charge billions upon billions of times per second. And because gluons carry color charge, they can emit and absorb other gluons. The gluon field inside a proton is self-interacting and turbulent. It's one of the most complex systems in nature, and fully solving the equations of quantum chromodynamics remains one of the hardest problems in theoretical physics. In fact, proving that quantum chromodynamics actually confines quarks, rather than just observing that it appears to, is one of the 7 Millennium Prize problems in mathematics, with a $1 million bounty for a rigorous proof. Now let's leave the strong force and turn to the weak force. The weak nuclear force is responsible for the processes that no other force can accomplish. It can change one type of quark into another. It's the only force that can transform the fundamental identity of a particle. This makes the weak force essential for nuclear reactions, radioactive decay, and ultimately for the existence of the elements that make up our world. The gauge bosons of the weak force are the W+ boson, the W- boson, and the Z boson. Like the photon and gluon, these are spin 1 particles. They arise from a gauge symmetry, specifically a symmetry group called SU2. But unlike the photon and the gluon, the W and Z bosons are massive, very massive. The W bosons have a mass of about 80.4 giga-electron-volts, and the Z boson has a mass of about 91.2 giga-electron-volts. To put that in perspective, these bosons are roughly 80 to 90 times heavier than a proton. They're among the heaviest fundamental particles known. The mass of the W and Z bosons has profound consequences. Remember the principle we discussed earlier. The range of a force is inversely related to the mass of its gauge boson. Massless bosons, like the photon, mediate forces with infinite range. Massive bosons mediate forces with short range. The heavier the boson, the shorter the range. The W and Z bosons are so heavy that the weak force has an extremely short range, about 1,000th of the diameter of a proton. That's why it's called the weak force. It's not actually weak in the sense that the fundamental coupling is small. The weakness comes from the fact that the massive gauge bosons can only mediate interactions over extremely short distances. At very high energies, when particles are close enough for the weak force to operate, the weak interaction is actually comparable in strength to electromagnetism. The W bosons are particularly interesting because they carry electric charge. The W+ has a positive electric charge and the W- has a negative electric charge. This means the W bosons participate in electromagnetic interactions as well as weak interactions. The Z boson, by contrast, is electrically neutral. This pattern, 2 charged bosons and 1 neutral boson, arises from the structure of the SU2 gauge symmetry. The most important thing the weak force does is change the flavor of quarks. In particle physics, flavor refers to the type of quark: up, down, strange, charm, bottom, or top. These 6 flavors come in 3 generations, each generation containing 2 quarks. The electromagnetic force and the strong force both preserve quark flavor. An up quark stays an up quark after an electromagnetic or strong interaction. But the weak force can change an up quark into a down quark, or vice versa, or change quarks across generations. This is what happens in beta decay, one of the most important processes in nuclear physics. In beta- decay, a neutron transforms into a proton. At the quark level, what happens is that one of the neutron's down quarks emits a W- boson and transforms into an up quark. The W- then decays almost immediately into an electron and an antineutrino. The neutron, which contained 2 down quarks and 1 up quark, has become a proton, which contains 2 up quarks and 1 down quark. A fundamental particle has changed its identity. The W boson was the messenger that made this transformation possible. This process is essential for the universe as we know it. Inside the Sun, nuclear fusion converts hydrogen into helium. One of the key steps in this process is the conversion of a proton into a neutron, which requires the weak force. Without the W bosons mediating this transformation, the Sun couldn't fuse hydrogen. It couldn't produce energy. Life on Earth wouldn't exist. The weak force, despite its short range and its subtle effects, is absolutely critical for the cosmos. The Z boson mediates a different kind of weak interaction called the neutral current. In a neutral current interaction, particles exchange a Z boson without changing their electric charge or flavor. These interactions are subtler than charged current interactions mediated by W bosons, but they're equally real and have been confirmed in numerous experiments. A concrete example is neutrino scattering. A neutrino can pass near an electron and exchange a Z boson with it, causing the electron to recoil. Neither particle changes identity, no charge is transferred, but momentum is exchanged through the Z boson, and the electron is knocked away. This kind of invisible nudge, mediated entirely by the neutral Z, was first observed at CERN in 1973 and was a major triumph for the electroweak theory, which had predicted its existence. Now, here's where the story of the W and Z bosons connects to a deeper puzzle. We said that unbroken gauge symmetries produce massless gauge bosons. The photon is massless because the electromagnetic gauge symmetry is unbroken. Gluons are massless because the color gauge symmetry of the strong force is unbroken. But the W and Z bosons are massive, very massive. If they arise from a gauge symmetry, and gauge symmetries are supposed to produce massless bosons, how can the W and Z bosons have mass? The answer is that the gauge symmetry of the weak force is broken. Not explicitly, not by hand, but spontaneously. Spontaneous symmetry breaking is a process where the underlying laws of physics have a symmetry, but the state the system actually settles into does not. The laws are symmetric, but the outcome isn't. A simple analogy is a ball balanced on top of a hill. The hilltop is perfectly symmetric. The ball could roll in any direction, but eventually the ball rolls down in one particular direction, breaking the symmetry. The laws governing the ball are still symmetric. The hill looks the same from every angle, but the ball's actual position is not. In the standard model, the symmetry of the weak force is broken by the Higgs field. The Higgs field is a quantum field that permeates all of space, similar to the electromagnetic field or the electron field. But unlike most fields, the Higgs field has a non-zero value even in its lowest energy state. Everywhere in the universe, at every point in space, the Higgs field has a constant non-zero value. This non-zero value is called the vacuum expectation value. It's as if the entire universe is filled with an invisible background of Higgs field energy. This background Higgs field interacts with the W and Z bosons. As these particles move through the Higgs field, they interact with it constantly, and this interaction gives them mass. The photon doesn't interact with the Higgs field in this way, which is why the photon remains massless. The W and Z bosons interact with it strongly, which is why they're so heavy. The Higgs field also has its own quantum, its own particle excitation. That's the Higgs boson. The Higgs boson was predicted in the 1960s and finally discovered at CERN's Large Hadron Collider in 2012. Its discovery confirmed the mechanism by which the W and Z bosons acquire their mass, and earned Peter Higgs and Francois Englert the Nobel Prize in Physics in 2013. But here's something critically important that I need to make very clear. The Higgs boson is not a gauge boson. This is a common source of confusion. The Higgs boson is a boson, yes. It has integer spin, but its spin is 0, not 1. It's a scalar boson, not a vector boson. It doesn't arise from a gauge symmetry in the way that the photon, gluon, and W and Z bosons do. It's not a force carrier. It doesn't mediate any of the fundamental forces. The Higgs boson is the quantum of the Higgs field, and the Higgs field is responsible for giving mass to the W and Z bosons, and to fundamental fermions. But the Higgs boson itself plays a completely different role from the gauge bosons. Lumping the Higgs boson in with the gauge bosons is a mistake, and it's one that many casual descriptions of particle physics make. The gauge bosons are spin 1 particles that mediate forces. The Higgs boson is a spin 0 particle associated with the mechanism of mass generation. They're different things with different roles, and this brings up an interesting detail about how the electroweak unification works. In the standard model, the electromagnetic force and the weak force aren't truly separate forces. They're two aspects of a single underlying force called the electroweak force. At very high energies, the kind of energies that existed in the first fraction of a second after the Big Bang, the electromagnetic and weak forces are indistinguishable. They're one force described by a single unified gauge symmetry called SU2 cross U1. This combined symmetry has 4 gauge bosons. As the universe cooled and the Higgs field settled into its non-zero vacuum state, the electroweak symmetry broke. 3 of the 4 gauge bosons acquired mass, becoming the W+, W-, and Z bosons. The 4th remained massless. That 4th boson is the photon. From one unified force, 2 apparently different forces emerged, distinguished by whether their gauge bosons picked up mass or not. Electromagnetism, with its massless photon, has infinite range and appears to be a separate force. The weak force, with its massive W and Z bosons, has an incredibly short range and appears to be a different force entirely. But at high enough energies, they reunify. They become one force again. This electroweak unification, developed in the 1960s and 1970s, was one of the greatest theoretical achievements in physics. Now, we've covered 3 of the 4 fundamental forces: electromagnetism with its photon, the strong force with its gluons, the weak force with its W and Z bosons. But there's a 4th force, the most familiar force in everyday life, the one that keeps your feet on the ground, holds the moon in orbit, and shapes the large-scale structure of the entire universe: gravity. Where is gravity's gauge boson? In principle, if we extend the logic of quantum field theory to gravity, there should be a gauge boson of gravity. It would be called the graviton. Based on the mathematical properties of gravity, the graviton would have to be massless, because gravity has infinite range. And it would have to have spin too, because gravity is described by a symmetric tensor field, the metric tensor of space-time. And the quantum of such a field has spin too. This makes the graviton different from all the other gauge bosons, which have spin 1. The graviton has never been detected, not even close. And there are fundamental reasons why detecting it might be effectively impossible with any technology we can imagine. Gravity is astonishingly weak compared to the other forces. The gravitational attraction between two protons is about 10 to the power of 36 times weaker than the electromagnetic repulsion between them. That's a 1 followed by 36 zeros. To detect a single graviton, you would need a detector so sensitive that it could register the tiniest conceivable quantum of gravitational energy. The interaction between a graviton and any detector would be so faint that it would be lost in the noise of every other interaction happening simultaneously. But the problem with gravity runs deeper than just experimental difficulty. When physicists try to build a quantum field theory of gravity using the same methods that work brilliantly for the other three forces, the theory breaks down. The calculations produce infinities that can't be removed. In quantum electrodynamics and quantum chromodynamics, infinities also appear in calculations, but they can be dealt with through a process called renormalization. You absorb the infinities into the definitions of physical quantities like mass and charge, and the remaining predictions are finite and meaningful. This is why quantum electrodynamics can make predictions accurate to 10 decimal places. But when you try to renormalize quantum gravity, it doesn't work. New infinities keep appearing at every level of the calculation. The theory is what physicists call non-renormalizable. It can't be made mathematically consistent using the standard methods of quantum field theory. This doesn't mean gravity can't be quantized. It means that the standard approach, the approach that works so well for electromagnetism, the strong force and the weak force, fails for gravity. Something else is needed. This is one of the deepest open problems in physics. How do you reconcile gravity with quantum mechanics? The two pillars of modern physics, general relativity and quantum field theory, are individually spectacularly successful. General relativity describes gravity as the curvature of space-time caused by mass and energy. It predicts black holes, gravitational waves, the expansion of the universe, and the bending of light around massive objects, all confirmed by observation. Quantum field theory describes the other three forces and all known particles with extraordinary precision. But the two frameworks are fundamentally incompatible. They use different mathematical languages, different conceptual frameworks, and different assumptions about the nature of space and time. String theory is one proposed solution. It suggests that all particles, including the graviton, are actually tiny vibrating strings. Different vibrational modes of the string correspond to different particles. One particular vibrational mode naturally gives a massless spin 2 particle, which is exactly what the graviton should be. This was one of the early reasons physicists got excited about string theory. It seemed to naturally include gravity, but string theory requires extra dimensions of space beyond the three we experience, and it has yet to make a unique, testable prediction that could confirm or refute it. Loop quantum gravity is another approach. It tries to quantize gravity directly by quantizing the geometry of space-time itself. In loop quantum gravity, space is not smooth and continuous, but is made of tiny discrete units at the smallest scales. This granularity of space-time might resolve the infinities that plague the standard approach. But loop quantum gravity has its own challenges and limitations. The honest truth is that we don't yet know how to build a complete quantum theory of gravity. The graviton almost certainly exists in some form, given that all other forces have gauge bosons and gravity exhibits wave-like behavior as confirmed by the detection of gravitational waves by the LIGO experiment in 2015. Those gravitational waves, ripples in space-time produced by the merger of two black holes, are the classical analog of gravitons. Just as electromagnetic waves are made of photons, gravitational waves should be made of gravitons. But we've never detected individual gravitons and may never be able to. So the standard model of particle physics describes three forces and their gauge bosons with extraordinary success. Electromagnetism with the photon, the strong force with 8 gluons, the weak force with the W+, W-, and Z bosons. Together, that's 12 gauge bosons. These 12 particles, along with the 12 matter fermions, 6 quarks, and 6 leptons, and the Higgs boson, make up the complete particle content of the standard model. Gravity remains outside this framework, awaiting a deeper theory that can bring it into the quantum fold. But even with this incompleteness, the gauge boson picture of forces is one of the most successful and beautiful ideas in science. 3 of the 4 fundamental forces are described by gauge symmetries. Each symmetry demands the existence of specific gauge bosons. Those bosons mediate the corresponding force through quantum exchange processes. The properties of each boson, its mass, its charge, its self-interactions, determine the character of the force it carries. Massless photons give electromagnetism infinite range. Self-interacting gluons give the strong force its confining behavior. Massive W and Z bosons give the weak force its short range. The universe, at its most fundamental level, is a system of quantum fields interacting through the exchange of gauge bosons. Every force you've ever felt, every interaction that has ever occurred, from the light of distant stars to the nuclear reactions that power them, from the radioactive decay that heats Earth's interior, to the electromagnetic bonds that hold the molecules of your body together, all of it is gauge bosons doing their work. Messenger particles flashing in and out of existence, carrying forces across the quantum fields that underlie everything. And the most remarkable thing about all of it is that these messengers don't exist by accident. They exist because they must. Because the symmetries that govern the laws of physics require them. That's the deepest lesson of gauge bosons. Forces aren't arbitrary additions to the universe. They're the inevitable consequences of symmetry, and understanding why that's true is the final piece of this story. We've spent this entire journey building up to something. We've explored what gauge bosons are. We've looked at their properties, their differences, their roles in mediating the fundamental forces. We've met the photon, the gluons, the W and Z bosons, and even the hypothetical graviton lurking at the edge of our understanding. But there's a question we haven't fully answered yet. The deepest question of all. Why do gauge bosons exist? Not just how they work, not just what they do, but why the universe requires them. Why reality would be impossible without them. And the answer to that question takes us to what is arguably the most profound idea in all of physics. The idea that forces are not added to the universe by hand. They emerge inevitably from symmetry. We touched on gauge symmetry earlier when discussing the photon. We said that if you demand the laws of physics remain unchanged, when you adjust the phase of the electron field independently at every point in space, the mathematics forces you to introduce the electromagnetic field. The photon must exist to preserve the symmetry. But now we need to understand this at a deeper level. Because gauge symmetry isn't just a mathematical trick or an abstract requirement that physicists impose on their equations for aesthetic reasons. It's connected to something fundamental about how the universe operates. It's connected to the idea that certain aspects of reality are redundant, that there's more than one way to describe the same physical situation, and that the laws of nature must respect this redundancy. Let's think about what symmetry really means in physics. At its core, a symmetry is an operation you can perform on a system that leaves the observable physics unchanged. Rotate a perfect sphere and it looks the same. Translate a set of physical laws to a different location and they work the same way. These are symmetries. The transformations change something about the description, but not about the physics. Global symmetries are the simpler type. You perform the same transformation everywhere simultaneously. Every point in the universe gets the same treatment. These symmetries are important and powerful. As Emmy Noether showed, every continuous global symmetry corresponds to a conserved quantity. We've already seen how this works for energy, momentum, and angular momentum. But the deeper lesson of Noether's insight is that conservation laws aren't imposed on nature from outside. They emerge automatically from the structure of the physical laws. They're consequences of symmetry, not assumptions bolted on after the fact. But gauge symmetries go further, much further. A gauge symmetry says that you can perform different transformations at different points in space and time, and the physics still doesn't change. This is a much more demanding requirement. To understand why, imagine you have a field, like the electron field, and this field has an internal property, like its phase, that you can adjust. A global symmetry says you can adjust this phase by the same amount everywhere and nothing changes. Fine. That's relatively easy to satisfy. But a gauge symmetry says you can adjust the phase by a different amount at every single point in the universe, independently, and nothing observable should change. The physics should be completely indifferent to these local adjustments. Now, why would physicists demand such a thing? Why insist on this seemingly arbitrary requirement? Because it turns out that gauge symmetry reflects something deep about the nature of physical description. In quantum mechanics, the phase of the wave function isn't directly observable. You can never measure the absolute phase of an electron's wave function. You can only measure relative phases between different states through interference effects. The absolute phase is what physicists call a gauge degree of freedom. It's part of the mathematical description, but not part of the physical reality. If the absolute phase isn't physical, then the theory shouldn't depend on it. The theory should give the same predictions regardless of how you set the phase. And if that's true locally, at every individual point in space, then you need the theory to be invariant under local phase changes. You need gauge symmetry. So gauge symmetry isn't an arbitrary imposition. It's a reflection of the fact that our mathematical description of the universe contains redundancy, extra information that doesn't correspond to anything physical, and the theory must be structured so that this extra information doesn't affect the predictions. But here's the remarkable part. When you take a theory that describes matter particles and you demand that it be gauge invariant, that it respect this local symmetry, the theory as it stands is incomplete. The derivatives in the equations which describe how the field changes from point to point in space are not gauge invariant by themselves. When you change the phase of the field by different amounts at neighboring points, the derivative picks up an extra piece that depends on how fast the phase is changing. This extra piece spoils the invariance. The equation changes. The symmetry is broken. The fix is elegant and profound. You replace the ordinary derivative with a new object called the covariant derivative. The covariant derivative includes an additional term, a new field that transforms in just the right way to cancel the extra piece introduced by the local phase change. This new field is the gauge field, and its quantum is the gauge boson. The gauge field is not something you add to the theory because you want forces to exist. It's something the theory generates on its own when you demand local symmetry. The gauge field is the mathematical compensation for the local redundancy in the description. And the interaction between the matter field and the gauge field, which emerges automatically from the covariant derivative, is what we experience as a force. This is why physicists say that gauge bosons are required by symmetry. They're not optional. They're not one possible way to build a theory of forces. They're the only way that's consistent with the gauge symmetry. Without them, the theory is mathematically inconsistent. The equations don't work. Predictions become meaningless. The gauge bosons are the price you pay for having a theory that correctly reflects the redundancy in the physical description. Or rather, they're not a price at all. They're a gift, because the forces they carry are what make the universe interesting. Now, each of the three forces in the standard model corresponds to a specific symmetry group. These groups are mathematical structures that describe the set of all possible gauge transformations for that force. Electromagnetism corresponds to the symmetry group called U1. This is the simplest possible gauge group. It describes transformations of a single phase angle. You can think of it as rotations around a circle. There's only one phase to adjust, so there's only one gauge field and one gauge boson. That gauge boson is the photon. The simplicity of U1 is why electromagnetism is the most straightforward of the fundamental forces. The weak force corresponds to the symmetry group SU2. This describes transformations among two related fields, essentially mixing two types of particles into each other. The mathematics of SU2 requires three gauge bosons. In the electroweak theory, before symmetry breaking, these three bosons are all massless. After the Higgs field breaks the symmetry, they become the massive W+, W-, and Z bosons. The third combines with the U1 boson to produce the massless photon and the massive Z through a process called mixing. The number of bosons, their charges, and their interactions are all determined by the structure of SU2. Physicists didn't choose to have three weak bosons. The symmetry group demanded exactly three. The strong force corresponds to SU3. This describes transformations among three color charges: red, green, and blue. The mathematics of SU3 requires exactly 8 gauge bosons, and those are the 8 gluons. Their color charge combinations, their self-interactions, their role in confinement, all of this follows from the structure of SU3. Physicists didn't design gluons to have these properties. The symmetry determined everything. Here's what makes this so powerful. The symmetry groups don't just tell you how many gauge bosons exist. They tell you everything about how those bosons behave. They determine the bosons' charges, their interactions with matter, their interactions with each other, their coupling strengths, and the entire mathematical structure of the force. Once you specify the gauge group, the rest follows. The properties of the photon are determined by U1. The properties of the W and Z bosons are determined by SU2 cross U1. The properties of gluons are determined by SU3. The symmetry is the blueprint. The gauge bosons are what the blueprint builds. This principle of symmetry dictating interactions is one of the most beautiful and powerful ideas in science. It means that the forces of nature aren't arbitrary. They're not random features that the universe happens to have. They're the inevitable consequences of the symmetries that the laws of physics obey. If you asked why the electromagnetic force exists, the deepest answer physics can give is because the laws of physics have U1 gauge symmetry. If you asked why the strong force exists, the answer is because the laws of physics have SU 3 gauge symmetry. The forces exist because the symmetries exist. And the symmetries exist because the mathematical description of reality contains redundancies that the physical predictions must be independent of. There's something almost philosophical about this. The universe seems to be built on the principle that nature hides unnecessary information. The absolute phase of a quantum field is unnecessary information. Nature hides it by making the physics invariant under changes in that phase. And the act of hiding that information, of maintaining that invariance, automatically creates the electromagnetic force. The force isn't designed. It emerges from the act of maintaining consistency. It's a consequence of the universe being self-consistent in the face of its own descriptive redundancy. Now, this success immediately raises a tantalizing question. If 3 of the 4 forces can be described by gauge symmetries, and if those gauge symmetries determine everything about the forces, could there be an even larger symmetry that encompasses all 3? Could there be a single gauge group that unifies the electromagnetic, weak, and strong forces into one? Electro-weak unification already showed that this kind of unification is possible. Before the Higgs field breaks the symmetry, the electromagnetic and weak forces are aspects of a single electroweak force, described by the gauge group SU2 cross U1. At high energies, these forces are indistinguishable. The Bosons and the photon are all part of the same family of gauge bosons. It's only at lower energies, after symmetry breaking, that they appear as separate forces with different properties. Could the same thing happen at even higher energies? Could the strong force merge with the electro-weak force into a single grand unified force? This is the idea behind grand unified theories, often abbreviated as GUTs. These theories propose that at extremely high energies, far higher than anything we can currently achieve in particle accelerators, the SU3, SU2, and U1 symmetry groups merge into a single larger symmetry group. The simplest proposal, put forward by Sheldon Glashow and Howard Georgi in 1974, uses the symmetry group SU5. In this theory, quarks and leptons aren't fundamentally different particles. They're different states of the same underlying field, related by the SU5 symmetry. The strong force, the weak force, and electromagnetism are all aspects of a single unified force, carried by gauge bosons of the SU5 group. Grand unified theories make specific predictions. One of the most dramatic is proton decay. In the standard model, the proton is absolutely stable. There's no process that can cause a proton to decay into lighter particles because there's no interaction that violates the conservation of barrier number strongly enough. But in grand unified theories, the larger symmetry group includes gauge bosons that can convert quarks into leptons. These hypothetical gauge bosons, often called X bosons and Y bosons, would be extraordinarily massive, with masses around 10 to the power of 15 giga-electron volts. That's 1 trillion times heavier than the proton. Because they're so heavy, their effects are incredibly suppressed at the energies we experience in everyday life. But they would allow protons to decay very slowly, with a lifetime of around 10 to the power of 34 to 10 to the power of 36 years. Experiments have been searching for proton decay for decades. The Super Kamiokande detector in Japan, a massive underground tank containing 50,000 tons of ultra-pure water, monitors the water for the faint flash of light that would signal a proton decaying. So far, no proton. decay has been observed. The current experimental lower bound on the proton's lifetime is about 10 to the power of 34 years, which rules out the simplest SU5 grand unified theory. But more complex grand unified theories predict longer lifetimes, and the search continues with ever more sensitive experiments. Another prediction of grand unification is that the coupling strengths of the three forces should converge at high energies. At everyday energies, the three forces have very different strengths. The strong force is the strongest, electromagnetism is intermediate, and the weak force appears weakest at low energies due to its massive bosons. But if you calculate how these coupling strengths change with energy, using the equations of the standard model, they evolve. The strong coupling gets weaker at higher energies. The electromagnetic and weak couplings change more slowly. If you extrapolate to very high energies, the three couplings approach each other. In the minimal, standard model without any extensions, they come close to meeting at a single point, but they don't quite converge. They miss each other slightly. However, in extensions of the standard model, such as supersymmetry, the couplings do converge at a single energy, around 10 to the power of 16 gigaelectron volts. This near convergence is considered suggestive evidence that grand unification might be correct, even though we haven't observed it directly. Beyond grand unification, there's an even more ambitious dream: unifying all four forces, including gravity, into a single theory. This would be the ultimate symmetry, the one gauge group that generates everything. Every force, every particle, every interaction in the universe would emerge from a single symmetry principle. String theory is the most developed candidate for such a theory. In string theory, all particles, including gauge bosons and gravitons, are different vibrational modes of tiny one-dimensional strings. The different forces emerge from different aspects of the string's behavior. String theory naturally includes gravity and requires gauge symmetries, making it a promising framework for total unification. But string theory remains unverified and faces significant challenges, including the fact that it exists in many different versions and makes very few unique predictions that could be tested with current technology. Still, the dream of unification is compelling. The history of physics has been a series of unifications. Newton unified terrestrial and celestial mechanics. Maxwell unified electricity and magnetism. Einstein unified space and time. Glashow, Weinberg, and Salam unified electromagnetism and the weak force. Each unification revealed that things that seemed different were actually aspects of a deeper unity. The pattern suggests that further unifications may be waiting. Let me step back and reflect on what we've learned, because the full picture is extraordinary. We started with the simple question of what a gauge boson is. The answer turned out to be far deeper than a dictionary definition. A gauge boson is a spin-1 particle that is the quantum of a gauge field. That gauge field exists because the laws of physics respect a local symmetry, a gauge symmetry, under which certain internal properties of matter fields can be freely adjusted from point to point in space without changing any observable predictions. The gauge field compensates for these local adjustments, maintaining the consistency of the theory. And the interaction between matter fields and gauge fields, which arises automatically from this compensation mechanism, is what we experience as a force. The photon is the gauge boson of the U1 symmetry of electromagnetism. It is massless, electrically neutral, and non-self-interacting. It gives electromagnetism its infinite range and its familiar inverse square law. The 8 gluons are the gauge bosons of the SU3 symmetry of the strong force. They carry color charge and interact with each other. This self-interaction creates confinement, trapping quarks permanently inside composite particles and giving the strong force its uniquely powerful short-range character. The W+, W-, and Z bosons are the gauge bosons of the SU2 cross U 1 electroweak symmetry, after that symmetry is broken by the Higgs field. Their masses, acquired through the Higgs mechanism, limit the weak force to an incredibly short range and allow it to mediate processes that change the identity of fundamental particles. The Higgs boson is not a gauge boson. It is a spin-zero particle associated with the Higgs field, whose non-zero vacuum state breaks the electroweak symmetry and gives mass to the W and Z bosons and to fundamental fermions. It plays a completely different role from the gauge bosons. The graviton, if it exists, would be the gauge boson of gravity with spin 2. But gravity has not yet been successfully described as a quantum gauge theory, and the graviton remains undetected. Every one of these particles exists because a symmetry demands it, not because physicists needed a way to explain forces, not because the theory required decoration or additional ingredients, but because the fundamental requirement of gauge invariance, the requirement that the physics be independent of local changes to unphysical degrees of freedom, generates these particles automatically. The gauge bosons are as necessary to the mathematical consistency of the standard model as the equal sign is to an equation. Remove them and everything falls apart. This brings us to the deepest point of all. Think about what it means that forces are consequences of symmetry. Every interaction that has ever occurred in the universe, every photon exchange between charged particles, every gluon bouncing between quarks inside a proton, every W boson mediating a nuclear decay inside a dying star, all of it is a consequence of the universe being self-consistent. Forces aren't imposed on reality from outside. They don't come from some external mechanism that pushes and pulls matter around. They emerge from the internal structure of reality itself, from the requirement that the mathematical description of nature must not depend on unphysical choices. When sunlight warms your face, that's photons being exchanged between the charged particles in the sun's plasma and the charged particles in the molecules of your skin. Those photons exist because the U1 gauge symmetry of electromagnetism requires them. When the sun fuses hydrogen into helium, the weak force converts protons into neutrons through the exchange of W bosons. Those W bosons exist because the SU2 gauge symmetry of the weak force requires them. When the protons and neutrons inside every atom in your body hold together, that's gluons maintaining the bonds between quarks. Those gluons exist because the SU3 gauge symmetry of the strong force requires them. You are held together by symmetry. The chair you're sitting in is held together by symmetry. The stars in the sky are burning because of symmetry. Every structure in the universe, from atomic nuclei to galaxy clusters, exists because gauge symmetries demanded the existence of messenger particles that carry the forces holding everything together. Forces don't just happen. They are conversations between quantum fields, mediated by gauge bosons that exist because the universe insists on being described consistently. The messengers aren't optional, they're inevitable. They're the universe's way of maintaining its own coherence. And that's what a gauge boson really is. Not just a particle, not just a force carrier. It's a piece of the universe's self-consistency, a quantum of the symmetry that underlies everything. It's the reason forces exist, the reason interactions happen, the reason the universe isn't just a collection of disconnected, non-interacting fields drifting through space with nothing holding them together and nothing connecting them. Without gauge bosons, there would be no forces. Without forces, there would be no atoms. Without atoms, there would be no stars. Without stars, there would be no atoms. Without atoms, there would be no stars. Without stars, there would be no atoms. Without atoms, there would be no stars. Without stars, there would be no atoms. Without atoms, there would be no stars. Without stars, there would be no atoms. Without atoms, there would be no stars. Without stars, there would be no atoms. Without atoms, there would be no stars. Without stars, there would be no atoms. Without atoms, there would be no stars. Without stars, there would be no atoms. Without atoms, there would be no stars. Without stars, there would be no atoms. Without atoms, there would be no stars. Without stars, there would be no atoms. Without atoms, there would be no stars. Without stars, there would be no atoms. Without atoms, there would be no stars. Without stars, there would be no atoms. Without atoms, there would be no stars. Without stars, there would be no atoms. Without atoms, there would be no stars. Without stars, there would be no atoms. Without atoms, there would be no stars. Without stars, there would be no atoms. Without atoms, there would be no stars. Without stars, there would be no atoms. Without atoms, there would be no stars. Without stars, there would be no atoms. Without atoms, there would be no stars. Without stars, there would be no atoms. Without atoms, there would be no stars. Without stars, there would be no atoms. Without atoms, there would be no stars. Without stars, there would be no atoms. Without atoms, there would be no stars. Without stars, there would be no atoms. Without atoms, there would be no stars. Without stars, there would be no atoms. Without atoms, there would be no stars. Without stars, there would be no atoms. Without atoms, there would be no stars. Without stars, there would be no atoms. Without atoms, there would be no stars. Without stars, there would be no atoms. Without atoms, there would be no stars. Without stars, there would be no atoms. Without atoms, there would be no stars. Without stars, there would be no atoms. Without atoms, there would be no stars. Without stars, there would be no atoms. Without atoms, there would be no stars. Without stars, there would be no atoms. Without atoms, there would be no stars. Without stars, there would be no atoms. Without atoms, there would be no stars. Without stars, there would be no atoms. Without atoms, there would be no stars. Without stars, there would be no atoms. Without atoms, there would be no stars, no stars. Without stars, there would be no planets. Without planets, there would be no life. Without life, there would be no one to look up at the sky and wonder why any of this exists. The next time you feel the warmth of sunlight, remember what's really happening. Photons, gauge bosons of the electromagnetic field, are streaming from the sun, traveling across 93 million miles of space at 300,000 kilometers per second, and being absorbed by the molecules in your skin. Each of those photons exists because of a symmetry principle that was established in the first fraction of a second after the Big Bang. Each photon is a messenger, carrying energy and information from one charged particle to another. Each one is a quantum of a field that permeates the entire universe. The next time you think about the atoms in your body, Remember that the nuclei at the centers of those atoms are held together by gluons exchanging color charge billions of times per second. Those gluons are confined inside the nucleus, never escaping, never being seen directly, but constantly working, constantly carrying the strong force that binds quarks into protons and neutrons and holds those protons and neutrons together despite their electromagnetic repulsion. The next time you think about the sun and why it shines, remember that nuclear fusion in the sun's core requires the weak force. W bosons, massive and short-lived, mediate the transformation of protons into neutrons, allowing hydrogen to fuse into helium and releasing the energy that lights up the solar system. Without those W bosons, fusion wouldn't work. The sun would be dark. Earth would be frozen. None of us would be here. Forces need messengers. That's the lesson. And those messengers, the gauge bosons, are the most fundamental reason why the universe has structure, complexity, and ultimately life. They exist because symmetry demands them. They work because quantum field theory describes them with breathtaking precision. And they matter because without them, there would be nothing. Nothing at all. Thank you for joining me on this journey through the deepest structure of reality. If you found this exploration valuable, a like or subscribe would mean a lot. It helps me keep making these deep dives into the fundamental nature of the universe. And the next time someone asks you what holds the universe together, you will know the answer. Not mysterious forces reaching through empty space. Not invisible hands pushing matter around. Gauge bosons. Messenger particles, born from symmetry, carrying forces between quantum fields, making the universe possible one interaction at a time. Good night.